So now that we've seen how to graph systems of linear inequalities, we can use this to solve our linear programming problems. We'll start out with a basic linear programming problem, set up the problem, and then we can see how this method of corners works in order to solve this problem. All right, so a linear programming problem, we said, consists of a linear objective function that's to be maximized or minimized, subject to certain linear inequality constraints. Okay, so here's an example of what you would see as a typical linear programming problem. We have a division of the Winston Furniture Company that manufactures dining tables and chairs. Each table requires 40 board feet of wood and 3 labor hours. Each chair requires 16 board feet of wood and 4 labor hours. The profit for each table is $45, while the profit for each chair is $20. In a certain week, the company has 3,200 board feet of wood and 520 labor hours available. So the question is, how many tables and chairs should Winston manufacture to maximize its profits? Okay, so breaking this problem down, we see that we have 2 things that the company's making. They're making tables and chairs, and each of those things requires 2 different constraints, right? We've got 40 board feet of wood and 3 labor hours for the table, 16 board feet of wood and 4 labor hours for the chair. Okay, so let's try to determine first what the objective function is. Okay, this objective function is what we're trying to optimize. Okay, what are we trying to do here? We're trying to maximize profit. Okay, so that means we need to find the profit function. Okay, so let's write that profit function down. That is P equals, okay, so what's our profit? Well, we make $45 for each table. So I'm going to say 45x, where x represents the number of tables, plus the profit for the chairs. We get $20 per chair. So we'll let y equal the number of chairs. Let me write down those variables just to remind us. X is the number of tables. Y is the number of chairs. Okay, now we have certain constraints that we need to follow, right? We cannot violate the requirements of how we're making these tables and chairs. Okay, so what's the restriction on the tables? We need 40 board feet of wood and 3 labor hours. And for the chairs, we need 16 board feet of wood and 4 labor hours. So our constraints are going to be, we're going to have 2 constraints. One for the board feet of wood that's required, and the other one for the labor hours. Okay, let me write this down. So we've got the board feet requirement, and then we've got the labor hour requirement. Because we have a limited number of board feet that we have available. Also, we have a limited number of labor hours that we have available. All right, we have 3,200 board feet of wood that we can use. Okay, so that means that if we have 40 board feet of wood that's used for the table, X, and we have 16 board feet of wood that's used for the chairs, for each chair, so 16Y, if we add those together, that cannot be more than 32 board feet. All right, so I can write that as 40x plus 16y must be less than or equal to 3,200, right? The total number of board feet of wood for the table, that 40x, plus the total number of board feet for the chairs, which is the 16y, cannot be more than 3,200. Okay, that's a constraint. That's that linear inequality constraint. We also have a constraint, a limitation on the labor hours, right? We only have 520 labor hours available. So if I do the same thing, if I take this 3x, right, there's 3 labor hours available for the table, and there are 4 labor hours required for the chairs, for each chair. If I were to add those together, that should be less than or equal to 520 labor hours. Okay, and we're going to have the next two constraints the same for all of these problems, to where x must be greater than or equal to 0 and y must be greater than or equal to 0, right? Because we're talking about the number of tables and chairs that's manufactured. Right? You cannot have a negative number of tables and chairs. Okay, so x and y must be greater than or equal to 0. All right, so this is our linear programming problem. We have our objective function and we have our constraints. All right, so now what we'll be able to do is graph the constraints and then use that feasible region, feasible set, to optimize and maximize the profit. Okay. All right. So let's look at how this works. We're going to need a theorem for this, and we'll establish this method of corners. All right. So this graphical method, the graphical approach for solving the linear programming problem. Each point in the solution region to the system of inequalities is a candidate to maximize, right? Once we graph the linear inequalities that we had, right, any point inside that set, after we graph the shaded region, could maximize the profit function. Okay, this is what's referred to as the feasible solution or the feasible set. The optimal solution, though, the one that actually does maximize this profit function, right, that's referred to as the optimal solution. And we're trying to find the optimal solution, not just a feasible solution. All right, so here's our theorem. Theorem 1 tells us that if a linear programming problem has a solution, then it must occur at a vertex or corner point of the feasible set. Okay, we're not going to try to prove this. We're just going to take it at face value and say this is true, that the optimal solution can only occur at a corner point, right? Which is why it's referred to as the method of corners. Okay, so here are the steps for the method of corners. Step 1, graph a feasible solution, just like what we did in the previous video. Step 2, find the coordinates of all the corner points. Then step 3, take those corner points and plug them into the objective function. And then step 4, the vertex that results in the maximum or the minimum, depending on the problem, for the objective function is the solution to the linear programming problem. Okay, let's see how this works in real time. All right, so going back to our example that we had at the beginning. We had established the objective function, the profit function, and our constraints. Okay, so now we can graph the linear inequalities to find the feasible set and then find the points of that, the corners of that feasible set. Okay, so starting with the first inequality that was found from the board feet, I can find the x-intercept by letting y equal 0. All right, so that's essentially just dividing the constant on the right-hand side by the coefficient of x, 3,200 divided by 40, which is 80. And the y-intercept is found by letting x equal 0, right, which is essentially dividing 3,200 by 16, the coefficient of y. That gives me 200. Right, so our y-intercept is 0, 200. And as far as the spacing for your graph, it's best to find the x and y-intercepts first so you can know how large to make your graph. I've got a 0, 200, so maybe I'll do this by 50s. And notice I'm only graphing the first quadrant because I know I have those restrictions, and I know I'm only working in the first quadrant, so no need of spending time with the other quadrants. All right, so let's graph this inequality. See 80, 0, somewhere between 50 and 100, maybe closer to 150, and 0, 200 would be here. All right, and drawing a line through these 2 points as best we can. Okay, and which way am I shading? Okay, use your origin, plug into that inequality, which means that the left-hand side is just going to give us 0, and we're just saying, is that a true statement or not? 0 is less than 3,200, so we will shade on the same side as that origin. Okay, now we'll do the same thing for the second inequality. We'll find the x-intercept by letting y equal 0. That leaves us with 520 divided by the coefficient of x, which is 3. That gives us, I'm just going to write that as 520 divided by 3 for my purposes. You want to at least get a decimal approximation so you know where to graph that. That would give you 173.33. But of course, that keeps repeating. I like to keep it as exact fractions rather than rounding as decimals. But 173.33, that's somewhere between 150 and 200. And then for the y-intercept, we'll do the same thing, letting x equal 0. And so that would give us, 520 divided by 4, which is 130, exactly. All right, so 130, somewhere between 100 and 150, closer to 150 than 100. All right, then draw a straight line through those 2 points as best we can. And again, we want to choose a test point, 0, 0. That sets the left-hand side equal to 0, and 0 is less than 520. So again, we'll shade below that red line. And our feasible solution is where you see the overlap of blue and red. I'll highlight that in black here. All right, so this is our feasible set. All right, and that theorem 1 tells us that the only points that could potentially maximize the profit occurs at these 4 corners. Okay, so we need to find what those 4 corners are. I know this one is 0, 0, which of course is not going to maximize the profit. This one right here, that was the 0, 130. And I know that this point here was the 80, 0. So the only point I need to actually find is this point here, and that's the intersection of the red and blue line. Okay, so I can find that using the elimination method or the substitution method. You know, some work should be done here. I'll use the elimination method. That may be a good thing to remind us of what that elimination method is, right? And you can use the Gauss-Jordan elimination if you wanted to, right? But we're trying to eliminate one of the variables by multiplying one or both equations by a constant. If I were to multiply that second equation by -4, that would give me a -16y, which will then cancel the y term when I add the 2 equations together. Okay, so that's -12x when I multiply by -4, and minus 16y equals -2080. Okay, so the y's cancel. 40x minus 12x is 28x, and 3200 minus 2080 is 1020. 1120, I should say. And so dividing both sides by 28, I get that x is equal to 40. So if x is equal to 40, I can plug that 40 back into either equation, and we can find what the y value is. I'll just plug into that first one because it's the first one. All right, so that is 40 times 40, that's 1,600. Subtract 1,600 from both sides. 3,200 minus 1,600 is 1,600. Divide both sides by 16, we get 100. Okay, so this point here is 40, comma, 100. Okay, so we have all four corners. Okay, so now we can evaluate the objective function at these corner points. Whichever one gives us the largest value will optimize our profit and will be our solution. Okay, and we said that 0, 0 is not going to maximize a profit, so we can skip that one. But we'll do this 0, 130. All right, so let's see, 45 times 0 plus 20 times 130 is 2,600, 2,600. Okay, and then 45 times 40 plus 20 times 100 is 3,800. And then the point 80, 0 is 3,600. Okay, and so out of those 3 points, right, disregarding the 0, 0 corner point, the corner that gives us the maximum profit is 3,800. Okay, so how many tables and chairs should Winston manufacture to maximize its profit? Well, it should make 40 tables, and it should make 100 chairs. And that will result in the maximum profit of $3,800. We'll see additional examples, but this is the method of corners. We graph the linear inequalities, we find the corner points, we plug the corner points into the objective function, and then we find whichever one maximizes or minimizes, depending on the problem, to find our solution.